The subject of linear algebra is really all about vector spaces, and those are what we're going to define in this video. The idea of a vector space is that it generalizes certain properties of ordinary column vectors. And the reason you want to do this is because it turns out that structures that obey the ordinary rules for vector addition and vector scalar multiplication crop up throughout mathematics, even in contexts that don't look at all like column vectors. And what we're going to find is when we've given our abstract definition of a vector space, we can prove lots of things about any vector space. So those things we prove will hold not just for column vectors, but for absolutely any vector space whatsoever, even ones which don't look at all like traditional vectors. So a vector space is supposed to generalize the idea of vector addition and scalar multiplication happening to column vectors. And when you do scalar multiplication, you multiply by elements of some kind of field. So to define a vector space, the first thing you have to do is to choose a field, and that field contains the scalars that you're going to be allowed to multiply by. So when we talk about a vector space over a field F, that F is some field like the real numbers or the complex numbers or one of the finite fields of order P we've been learning about recently. And saying something is a vector space over a field F means that when you do scalar multiplication, you can multiply by any element of that field F. So if we talk about a real vector space, it means you can do scalar multiplication by a real number. If we talk about a complex vector space, it means you can scalar multiply by complex numbers. Or if we talk about a vector space over the field with 5 elements, it means you can do scalar multiplication by an element of the field of 5 elements. So an F vector space, or a vector space over the field F, is just a set which has got an addition operation, which we usually write with an ordinary plus, a scalar multiplication operation, which allows you to multiply elements of your vector space by elements of your field F, and a zero vector, which we usually write like this. And to be a vector space, you have to have those 3 things and then obey each one of these 8 rules called the vector space axioms that I've written on this slide. Now, I don't really want to talk about all of these 8 axioms in depth. What I would like to do is just highlight that the set R to the n, so all height n column vectors for some particular number n, with the usual vector addition and scalar multiplication, satisfies all of these properties. So what that means is that R to the n is a vector space over the real numbers. So you can multiply by real numbers. It wouldn't be, for example, a complex vector space, at least not in any obvious way, because you can't scalar multiply a real vector by a complex number and get another real vector. So it will be a real vector space in this case. So let's just look at a couple of these axioms just to see why they really are familiar properties of vector addition and vector scalar multiplication. So if we took, for example, property 3 says that in a vector space, your addition operation must be associative. And for sure, the normal notion of adding column vectors is associative. Or if you look at property 5, for example, it says when you scalar multiply by the number 1, and every field has to have a 1 element, well, if you scalar multiply by the number 1, then you don't change the vector that you scalar multiplied. And again, this is definitely true for the ordinary notion of scalar multiplying a column vector by a number. Let's look at a different one. So property 8 is a distributivity law. And again, this is a standard property for column vectors. Or if we look at property 2, that's about additive inverses. It says that for any vector v, there must exist another vector x such that when you add x to v, you get the 0 vector. Well, that's certainly true for column vectors, because if you give me, let's say, n equals 3, and you give me the column vector 1, 2, 3, then there is another column vector which you can add to that and get the 0 vector, namely the column vector -1, -2, -3. So these are the vector space axioms. And as I was saying just now, these things generalize the situation for ordinary column vectors, but there are many other examples of things which obey all the vector space rules despite not actually being themselves vectors. So let's start with some examples which are familiar to you already, and then we'll look at some slightly more unusual examples later. So for example, as we've just said, r to the n with the usual addition and the usual scalar multiplication is a vector space over the real numbers. So sometimes instead of saying a vector space over R, people will say a real vector space. It means the same thing. Okay, all of those 8 properties were true for R to the n with its usual scalar multiplication by real numbers and its usual vector addition. And of course the same thing happens for C to the n. That is a vector space over the complex numbers. Okay, for exactly the same reasons. All of those things were familiar properties of real or complex vectors. So what we would say in this case is a complex vector space. So when you say something is a complex vector space, you mean it's a vector space over the complex numbers. In other words, you are allowed to multiply by any complex number as a scalar. Okay, well, what else? You can generalize this a little bit further. We've met various different examples of fields. So, of course, you can form column vectors over any field. So f to the n is a f vector space for any field f. And f to the n, of course, just means the space of all height n column vectors with entries from this field f. So we could form, for example, if we took f to be a finite field, we could form a vector space of column vectors with entries from the finite field with order 5, for example, and that would be a vector space where you could do scalar multiplication by elements of the field of order 5. Okay, let's look at a slightly different example, so something which is not just column vectors. So let's have vector spaces consisting of matrices. So I'm going to write m by n of f. What I mean by this is all m by n matrices whose entries belong to f. So if you choose a field f, then this will be an f vector space. Or a vector space over f. So the set of m by n matrices with complex entries will be a complex vector space, and the set of m by n entries whose entries belong to the finite field of order 2 will be a vector space over the finite field with order 2. And let's look at one final slightly silly example, which is you could take just the set containing something we'll call 0v with addition defined by 0v plus 0v is equal to 0v, and scalar multiplication, well, for any lambda, lambda times 0 is equal to lambda 0 is a real vector space. Or, if you like, it's a complex vector space, if you just make the same definition for complex numbers, or vector space over any field you like. So this is called the 0 vector space. It gives us a degenerate example of vector spaces. So let's look now at some more strange-looking examples. So I want to make it clear that the elements of a vector space don't have to be vectors. They don't even have to be anything that's vaguely connected to vectors. They can be anything at all. And that's why the concept of a vector space is so useful, because it comes up everywhere in mathematics. So, for example, let's look at some polynomials. You've met polynomials in analysis, for example. So R of x, so R with square brackets and then x, means all polynomials in one variable x. So let's say a0 plus a1x plus and so on up to am x to the m for m some natural number, and a0 up to am in the real numbers. So here x is some kind of variable, some kind of indeterminate. Then this is a real vector space. So to define a vector space, you have to say what the zero vector is and what the addition and scalar multiplication are. So we just give it the usual polynomial addition. And multiplication. And the zero vector, of course, would just be the zero polynomial, the constant polynomial, which is the value 0 everywhere. So, I mean, what would happen in that vector space is literally just the normal things that happen when you multiply by scalars and when you add polynomials. Like, for example, x squared plus 2 would be in this thing, and so would 1 plus x minus x cubed will be in there. And you can add things like this. That's another legitimate polynomial. And you can scalar multiply things like this. So if you multiplied 2 into x squared plus 2, you do get another polynomial. You get the polynomial 2 times x squared plus 4. And the zero vector exists, so the zero vector in this case will be the constant polynomial, which is 0 everywhere. So this set of polynomials, which has on the face of it nothing to do with vectors, really does give us an example of a real vector space. And equally, another one which will be useful to us is we can just think about the polynomials of degree less than or equal to n. So I'm going to write this to mean all of the polynomials with degree at most n. So a0 plus a1x plus and so on. So the same definition as before, only we just go up to an x to the n for some fixed n. So this time a0 up to an have to be real numbers. Okay, and again, if you add two elements in there, using the usual polynomial addition, you get another polynomial with degree at most n. So you can do addition, and you can do scalar multiplication, and there is a zero vector, the constant polynomial 0, and it obeys all of those familiar rules, which were the vector space axioms. So this is another example. So let's look at a slightly stranger example. Let's take, for example, I'm going to call this curly f like this. This is going to be all functions from the real numbers to the real numbers. Absolutely every function from the real numbers to the real numbers. If I want this to be a real vector space, I've got to say what the addition and the scalar multiplication are. So this is a real vector space with addition. Well, I have to define a way to add two functions. So I'm going to define, given two functions f and g, I'm going to define f plus g to be the function which takes x to f of x plus g of x. And I also have to say what the scalar multiplication is. So if you give me a function f and a real number lambda, I have to say what function lambda f is. So I just define it to be the function which sends a number x to lambda times f of x. Okay, and this is another legitimate real vector space. The 0 vector in this case would be, and I should also say what this is, so let's just put this in with 0 vector. So what should it be? It should just be the constant function 0 again. So 0 under 0f, which is the function which is just always 0, the constant function which is always 0. So this is another example which obeys all of the vector space axioms. It is another example of a real vector space. And of course, if you took the functions from the complex numbers to the complex numbers, you could make that into a complex vector space in a similar way. And things can be even more interesting than this. Actually, you'll see on one of your courseworks that there is an example of a game which you might have seen, so a kind of simple, really one of those casual games called Lights Out, where the game takes place on a square grid like this, and in the grid some of the squares are lit up. So maybe this one is lit up and this one is lit up, and you can click on some of the squares, and when you click on a square, some of them light up and some of them switch off. So here the black squares are supposed to be switched off and the yellow squares are supposed to be lit up, and the aim of the game is to make all the squares turn off. So that's why the game is called Lights Out. Anyway, it turns out that a good way to understand the game Lights Out is to understand the configurations in the game as elements in a vector space over the field with 2 elements. And if you want, you can check that out, learn a bit more about it on the coursework for this section.